So you can share the screen.
Good afternoon, everybody. Today's talk on our recently published work in the IEEE Proceedings is based on cybersecurity for the future of manufacturing. The work is a joint collaboration between Texas A&M University and New York University. Myself, Akash Theory, and Priyanka Mahesh are graduate students. Dr. Jen was a postdoctoral researcher in cybersecurity at the time. Dr. and Dr. Bukapatnam are experts in manufacturing and material science. Dr. Curry and Dr. Reddy are experts in cybersecurity. And Dr. Kumar is an expert in cyber physical systems and the application of the dynamic watermarking technique. We would like to thank sponsors who support us during the course of this work. Now, the cybersecurity needs for manufacturing is driven by the future of manufacturing, and the future of manufacturing is headed along two directions. It's democratization and digitalization. Now, the democratization of manufacturing refers to the idea of trying to make manufacturing available to all. And what this means is that it's not just the big businesses, the original equipment manufacturers that can avail manufacturing services, but it's also smaller businesses and new startups who can fabricate their parts for their activities. Now, this is being made possible because of the existence of a digital business supply chain. Now, the idea of democratization is very similar to what Uber has done to public transit. So folks in manufacturing are calling this as the Uberization of manufacturing. Now, the digitalization of manufacturing refers to the computerization of the different phases of manufacturing. For example, in the design phase, we observe that the manufacturing process workflow is being digitized. In the manufacturing phase, what we see is that the actual manufacturing plant flows, they bring in new technologies that operate in an interconnected manner. For example, the different manufacturing machines, sensors, actuators, controller PCs share a common plant flow network. Now, in addition, there's also an existence of a digital thread that connects the different phases of manufacturing with the digital business supply chain. Next. One of the efforts of digitization is the achievement of autonomy. If not done right, the manufacturing systems can be plagued by cyber attacks. We can observe this by learning from the automated manufacturing system. So in the past decade alone, there have been dozens of attacks that were made public. And the impacts of these attacks include both financial losses and some include terrible accidents too. Now, the medium scale enterprises are sometimes the weakest links in the supply chain, that's the assets of the supply chain participants. The 2019 Norsk Hydro attack is one such instance where through an email communication between the MSC and the OA, the attacker was able to get into the actual manufacturing plant flow and halt the production. Now, the shift from automation to autonomy is done by various technologies, and one of the technologies that is enabling it is the IoT device. The IoT devices have proved their success not only in manufacturing but in other industries too. Over to you, Priyanka.
As rightly mentioned by Akash, factories of the future are currently moving from automation to autonomy. And to enable that, IoT is being highly used in various industries, for example, manufacturing, energy, and resources. They're being used in various methods like connected product, connected assets. And these are basically used to accelerate predictive and preventive maintenance, supply chain, logistics, and also operational efficiency. To focus more on manufacturing, where we are using to lower manufacturing costs and enable new lines of business to improve overall productivity, IoT has become pivotal to maintain the competitive edge within manufacturing. IoT sensor networks and reliable connected assets are enabling the success of remote operations, even during the COVID crisis that we noticed. With real-time data, businesses can better monitor assets, products, as already mentioned within connected product, connected assets. So they use it to optimize the use, better anticipate machinery, better anticipate impending, I would say, impending failures, and identify root causes within the, if any failures occur, if any failure occurs within the manufacturing plant. Predictive condition-based maintenance are also being performed within the manufacturing industry, where they reduce costly downtime and repairs. For instance, an example would be autonomous vehicles, where they're connected to share information from onboard sensors, even from smartphones of pedestrians and cyclists, traffic sensors, and parking detectors. So all of these use cases within manufacturing actually enable them to better improve their efficiency and productivity. And even with other business sectors like military and to enable smart cities, we see wide-scale adoption of IoT to enable companies to acquire vast amounts of data from their assets, people, and processes, in turn improving again operational efficiency to better serve customer demands. So moving from success of how IoT devices have been implemented within various business sectors, we want to move to how various other technologies enable the success of IoT devices. So as we move towards future of manufacturing, new technologies are presenting promising opportunities for improvement across businesses of all sizes, from MSCs to large-scale enterprises. The usage and development of cobots, for instance, and autonomous mobile robots within factories are accelerating faster than ever. So these use cases actually help humans help humans in performing certain manual tasks that was earlier time consuming, thus reducing the lead times. Manufacturers are also using blockchain, cloud, and machine learning to develop implementations that have potential to help them streamline operations, gain greater visibility into the supply chain, and also track assets with precision, I would say. IIoT is helping transform linear supply chains into digital supply chain networks, where we notice that it is helping in developing the digital thread across various business sectors and even with customers and suppliers. Although we see a lot of collaboration across these technologies that I just mentioned with AI, ML, blockchain, we notice that certain technologies like cobots, which is very new within the manufacturing line, is that they do help humans empower, like in the manufacturing process with, for example, Amazon's and the Walmart helps use cobots for picking and packing of goods that is usually prone to human error. And so cobots fulfill these tasks and avoid any mistakes or even reduce the lead times. But there are risks involved. Like, for example, these machines can be remotely tampered to alter safety configurations and also prevent them from operating outside like a designated safety boundary. For example, these cobots have built-in camera and microphones that could be accessed and used for commercial espionage if a vulnerability can be exploited. But it's also important, when we know these risks can be possible, it's important to understand the countermeasures and implement them within the shop floor environment. Like, for example, we can monitor the cobot behavior and also detect or report any odd behavior by sending in information from the cobot using the sensors again. So sensors can also be used to identify any odd behavior within the cobot. And I would say it's also important to update the cobot firmware from time to time. As soon as a update is available, that would enable having a robust process in maintaining security within the shop floor environment. And given that with the AMRs, we know that they are useful in navigating through the shop floor, avoiding any collisions, and also improving the lead time as such. But there are certain risks involved, like attackers can fabricate harmful sensor values and feed them to the robot control program. But again, it's important to identify certain countermeasures, like hardware devices like AMRs in this case have unique physical characteristics. With sensors, it is the sensor latency or the response time. So it is possible to a robot AMRs can actually detect the latency time. Given using ML, they can learn the sensor latency and they can detect an attack if a wrong latency value is given to them. So this would help detect any harmful sensor values and avoid attackers from providing any harmful sensor values.
Thank you, Priyanka. Now, um, um, with the movement towards the future of manufacturing, we see that manufacturing is bringing all these new technologies and operating in a very connected manner. So, along with the along with the efficiencies that are being brought in, these technologies also come with their vulnerabilities. Now, when operating in a connected manner, these vulnerabilities become complex. So to study these complex vulnerabilities, it is important to have a systematic approach to study the vulnerabilities. In the paper, we have developed an attack taxonomy to study these complex vulnerabilities. The taxonomy was developed keeping in mind the needs of manufacturing cybersecurity. So our attack taxonomy includes attack goals, attack methods, and attack targets. Now, attackers can target any phase of manufacturing uh, to uh, to cause a successful attack and go undetected. The attacks could happen either in the design phase, manufacturing phase, or both. What we learned from this attack taxonomy is that attacks that have occurred in the past on automated manufacturing systems observed very limited pathways. Let me give you an example. In the case of the German steel mill attack, the goal of the attacker was to sabotage by reducing the reliability of the manufacturing machine. In the case of production systems and assembly lines, the goal was again to sabotage, but this time by introducing a denial of service attack on the manufacturing machine. These are just two attack pathways. We have identified that there are several attack pathways that the attackers can take to achieve a successful attack. To prevent against these, we also identified the countermeasures that have proven to be successful uh, in securing other hardware. These countermeasures are applicable to different attack targets. However, although these countermeasures are effective, they are not an exhaustive list. Improving existing countermeasures, developing new countermeasures, and mapping the countermeasures to the attack targets in manufacturing remains a recent and a fairly active field of research. Now, the goal of studying manufacturing vulnerabilities and discovering cybersecurity solutions requires a test bed. That's because doing the testing on actual systems in factories is going to be very expensive. One such excellent exemplar that is aimed towards this goal is the Smart Hybrid Machine Tool Test Bed, the SHM Test Bed. The SHM Test Bed embodies the future of manufacturing, and why it does that is on a higher level, it is capable of executing complex process chain and achieve localized production. At lower levels, it's able to realize various thermodynamic pathways. It is also able to cater to the batch of one custom manufacturing. And how it is able to do is because of three elements: the hybrid element, the smart element, and the controller element. Now, what is the hybrid element? The hybrid element is referring to the manufacturing capabilities such as milling, grinding, polishing, and additive manufacturing, all present within one single machine. And this enables to achieve the localized production, which would have otherwise required a manufacturing cell with multiple machines. Now, what is the sensing element? The sensing element refers to the IoT devices that are connected to the machine to monitor the process that's happening. Now, with these three elements, the sensor element, the hybrid element, and the control element, what we can do is we can develop a closed loop process control. In the closed loop, bringing it back to the context of cybersecurity, using this closed loop process control, we can identify several vulnerabilities in the closed loop schematic itself. These vulnerabilities have been identified and presented in detail in the paper that we published. But let me give you an example of the impact of attacks on these vulnerabilities. That could be a failure of part during operation, that could be reverse engineering attack, and that could also be introduction of micro and macro defects, which will be hard to identify until the manufacturing process is complete. Over to you, Priyanka, again.
Thank you, Akash. Actually, in an attempt to bridge the gap between how we speak about identifying vulnerabilities between IT and OT environment, we introduce a three-tiered architecture, which enables manufacturers to gain a high-level holistic view of how information is flowing from each layer or tier to another. So if we talk about just tier 1 or L1 layer, where the device is IoT or IoT device or the smart sensors are present, we know that these are interconnected to each other. For example, a smart control thermostat or light turns on and off because they connect with each other, or the devices within a shop floor are connected to each other to save energy costs. So in this case, in the tier 1, when the devices are connected to each other, certain vulnerabilities could be web interface, the memory itself, physical interface, or the network services. Attackers can also take advantage of insecure default settings, outdated components, and unsecure update mechanism, among other things. Countermeasures in this place is watermarking of control signals in the production. This method prevents information from sensors or actuators from being intercepted by attackers, or using a very small secret signal. That's why it's called watermarking. And because these devices are connected to each other, we suggest that the segmentation of network should be in place, because there's a diverse device population in this layer. And the next layer that we want to talk about, or tier, is where people and IT play a role in digitizing manufacturing processes. So the L1 devices can be connected to L2 using field gateways that could be incorporated in place. Like, for example, many manufacturers use platforms like Power BI to extract information from sensors or actuators or machines, in fact, about how many products were manufactured, how many were discarded, how many were dispatched. All of this information can be relayed from L1 to L2 layer. Attackers in this layer signify that gaining unauthorized access on a network. Threat actors can also steal information on equipment behavior from measurements and data usually collected by their sensors. Countermeasures that we suggest using the study that we performed were obfuscation, which helps maintain security of design files, embedding codes. It's possible to embed serial numbers and barcodes on manufactured parts. For example, RFID. Fingerprinting can also be used for file authentication in manufacturing process chain. So the last layer that we're talking about is the L3 layer that supports both L2 and L1 layer in terms of any on-prem data center or cloud services that the manufacturing facility uses. So in this case, for example, risk could be if they're using mobile manufacturing, that holds tremendous advantages within the shop floor. But as business adopt cloud services, the mobile data could be unsecure and could also have unintentional backdoors to sensitive data. Countermeasures, again, in this place would be suggesting segmentation of how the networks are probably zoning of data, like zoning of segments or networks of data. And so once we have this in place, we want to understand better how all of this could be put into application. So in the next slide, we actually show how, I want to understand how threats within the smart manufacturing systems could be handled. So there's a vast amount of data generated by these devices from vehicle to plant manufacturing or building. So it's important to secure the data. So if we talk about just connected devices that talk to one another when they do data transfers from one point to another. So we want to ensure that security is in place, and not just connected devices. We talk about network access control and remote access control in particular, because these are certain controls that need to be essentially in place for the future of manufacturing. So when we talk about connected devices, OTA patching can be done for new devices and improve product behavior even after like the device is in the end user's hands. So from when the information is then relayed from the devices to the cloud, we want to ensure that secure communication is in place that will enable secure transfer of data from the devices to the cloud. So the for example, end-to-end encryption can be in place from device to the cloud. And within the cloud itself, it's essential to have cloud security controls in place that can be taken care by, that will be mostly taken care by cloud service providers, but performing like a cloud risk assessment beforehand would definitely help in this transition. And having DMZs in place also helps in securing confidential data. Organizations can also keep remote access controls or any other external communication security by using strong firewalls, encryption, authentication, intrusion detection, like even within the shop floor devices when the device is connected through the cloud to software applications. So having all of these in place can prevent from attacks like man-in-the-middle attack. Although we have scalable cloud-based analytical abilities that help in accessing information by third-party vendors, developers, programmers, and even OEM suppliers, it's essential to have identity and access management controls in place, which helps securing communication between all of these parties to the application itself or the interface itself. So I think so to conclude, we want to highlight certain key takeaways that we mentioned the security controls here.
Thank you, Priyanka. So now, in summary, what we see is the future of manufacturing is headed towards democratization and digitalization. To achieve these two directions, new technologies are being brought into the manufacturing system, and they come with their vulnerabilities. So now attackers can employ several novel attack pathways to execute a successful attack without being detected. To address these, we have come up with an attack taxonomy that allows us to systematically address these complex vulnerabilities that's arising in the manufacturing system. Priyanka?
Sorry, I was on mute. Yeah, so I was just saying that each organization does not even not only has to look at the cybersecurity risk as it applies to itself, because each one is very unique in terms of how they architecture and have security controls in place. With this era of connected manufacturing that is working, like you have to connect with suppliers and OEM or manufacturers. So adopting security controls that helps enable the digital thread would be essential. Also, we want to ensure that integration of existing security measures to create a real-time intelligence in order to identify threats and risks beforehand, so that that is also termed as predictive and preventive measures that the organizations take. Standard security measures could be incorporated into the tiered or hierarchical architecture, and a security assessment should be performed to identify underlying threats and countermeasures. And that's why we introduced the tiered architecture to help organizations understand the security defenses that they have in place, and also identify devices that can be grouped together. So thank you so much. We are available to any questions that you all have.
Thank you, Priyanka and Akash.